Welcome back. Today, let us continue with lesson number 8 of Unit 2, which we are going to discuss about Fourier transform of a periodic or non-periodic signal and convergence of Fourier transform. So, after completing this lesson, students will be able to derive the steps involved in obtaining the Fourier transformation of a non-periodic signal from Fourier series of a periodic signal. Categorize the conditions to be satisfied for obtaining the Fourier transform using Dirichlet conditions, which can also be mentioned as convergence of Fourier transform. The conditions which are resultant to obtain a convergence of Fourier transform. So let us discuss about the obtaining or representing a Fourier transform of non-periodic function. Consider an arbitrary signal x of t with a fundamental period of capital T as shown below. The spectrum for above signal will be a discrete one with spectral lines at different frequencies with adjacent to each other, separated by a frequency interval of f naught. So as from the figure we can see that graph is non-period because we are not mentioning that at which instant the signal is being obtained. We are mentioning that width of the pulse is having a period of t, but at which instant these pulses are coming, that is not clear. So this is considered for a non-periodic function, and the resultant of this given non-periodic function respect to arbitrary spectrum for different time instants has been represented here. With different frequency options, we can see the pulse width among the different spectral lines is reduced. As t increases, the width of the samples is reducing. So how we are going to derive the expression for obtaining Fourier transform of a non-periodic signal? So let us consider x of t be a non-periodic function and x suffix t of t be a periodic with period t. And the relation is given as x of t is equals to limit t tends to infinity xt of t. And the Fourier series of periodic signal, here as earlier we discussed the Fourier transformation t tends to infinity condition also we mentioned earlier. So we need to give a limit where t time period is applied to infinity because we need to map or we need to obtain the series or we need to transform the signals to an infinite time. So if I consider for infinite time, whatever be a type of a non-period, that will become periodic because at an infinite time it may appear one more time. So for that reason we are considering infinite. So in this Fourier transform is the main point is application of t to infinite value Okay, now Fourier series of a periodic signal, as you know, according to complex what to say according to exponential Fourier series formula, we have summation equals minus infinity to infinity c suffix n e power j n omega naught t, where c in 1 by t integral x of t into e power minus j n omega naught t, and omega naught t equals to 2 pi by t. These are already discussed, but the main difference is here the considered function is x suffix t of t. Only the difference is x suffix t of t. And then c suffix n represents the amplitude of the component of frequency in omega naught. And according to this, we already discussed what is a cn and tcn. We are rewriting the function with the integral limits from minus t by 2 to t by 2 as we are measuring the time period over a t. So for that reason, we are defining the integral value within the time period. Now, to obtain the Fourier transformation, we need to apply t value to infinity and on omega naught to omega. So if I consider these values, substitute these t value in omega naught, we get omega naught equals to 0. So If t are applied as an infinity, omega naught will become 0. So and discrete Fourier spectrum becomes continuous. Okay. Now further the summation becomes integral and xt of t will be x of t. So representation of x of xt of t to x of t and integral will to be as a summation. The function can be rewritten as here Tcn is applied with respect to limit t tends to infinity, n omega naught replaced with omega, and the function balance function is applied with respect to limit condition taken within the xt of t function and integral outside the function. So frequency spectrum of x of t can be represented as this limit t tends to infinity xt of t is replaced with x of t integral minus infinity to infinity e power minus j omega t dt, which is nothing but Tcn. So we are considering again one equation to Tcn, which is called as a spectral density function. So spectral density function is nothing but integration from minus infinity to infinity of given function t power minus j omega t dt. Here from this equation x of omega is called as a Fourier transform or Fourier integral of x of t. So you need to remember the formula of Fourier transformation of given x of t, which is given in the box. So rewriting the expression of x of xt of t in terms of exponential Fourier series, summation equal to minus infinity to infinity c sub x n e power j n omega naught t, where cn is given as x omega by t. So x omega by t is a rewritten term on place of cn and the remaining terms as it is. So as we already discussed, omega value as 2 pi by t. So t gets cancelled, the remaining term 2 pi will be the resultant existing in place of. So t gets cancelled, x of xt of t will become summation n equal to minus infinity x of omega by 2 pi into e power j n omega naught t into omega naught. So I think there is not any omega naught. Yeah, there is an omega naught. Okay, t expression is t 2 pi by omega. Yeah, t expression is 2 pi by omega naught. So we are rewriting the t expression as 2 pi by omega naught. So 2 pi in the numerator part will be omega naught. So therefore x of t is rewritten as limit t tends to infinity 1 by 2 pi summation equals to minus infinity to infinity x of omega into e power j n omega naught into omega naught. So as t tends to infinity, omega naught equal to 2 pi by t becomes infinitesimally small and may be represented by d omega. Also summation becomes integration. So as t tends to infinity, we can rewrite this limit condition and summation and combine with an integration and omega naught with the term d omega. This will be our inverse Fourier transform of a given x of t signal. Okay. Next, for x of omega and x of t are known as Fourier transform pair and can be written as x of omega is equals to Fourier of x of t or x of t is equals to Fourier inverse Fourier of x of omega. So in transformation, Fourier transform pair can be represented as a bidirectional arrow with ft represented on top, which indicates the Fourier transform. So x of t Fourier transform is x of omega and x of omega inverse Fourier transform is x of t. So what is the existence of Fourier transform? The existence of Fourier transform is the condition for which the signals are said to be can have Fourier transform. So this can consider as a convergence of Fourier transform and or Dirichlet conditions also of a Fourier transform. So Fourier transform doesn't exist for periodic functions and the conditions for function x of t to have Fourier transform. As they are called as Dirichlet conditions and or convergence of Fourier transform. So if these conditions are not satisfied, so Fourier transform may not exist for even for a periodic function also. So what are those? So x of t is absolutely integrable over the interval minus infinity to infinity. That is my integral minus infinity to infinity. X of t dt must be less than infinite, and x of t have a finite number of discontinuities in every finite interval, and further these discontinuities must be finite. X of t has a finite number of maxima and minima in every finite time interval. As these type of conditions are sufficient but not necessary, the Fourier transform will exist for functions which satisfy above conditions. So this is how the conversions of Fourier transform. With this we end this lesson. Let us meet for the next lesson. Thank you for watching.